Okay, time's 9:30, so let's begin here. So for today, you need to examine two subsections in the notes. The first one dealt with this thing called a drift term. This is not a common topic in a time series analysis course. In fact, I think it's just the second time I've ever taught it. But the authors of our book think that this is important, and until I have seen that in some of their later editions, I never even really thought about it before. And this drift term, which we call delta, is a parameter that we want to estimate. And the way that you can think about it coming about is if we consider, let's say, just a regular old ARIMA model, a 0-1-0. This also has a special name called a random walk model. And this model, you could first write it in this form here, where you have 1 minus b times x of t, subtract off the mean, if it was a non-zero mean, which most of the time would be, is equal to wt. And so if you go through a little bit of the math, you get then this, which then leads you up to this there. So you have x of t is equal to x of t minus 1 plus wt. Now, where the drift term comes in is that you have exactly the same model, but now we're also adding in this extra parameter that we would like to estimate. Okay? So before, with the regular ARIMA model, with that first differencing, basically what that is meaning is that those first differences themselves, x of t minus 1, has a mean of 0, because that mu falls out. But now, with this kind of a model, even if you have differencing, you now still have this extra parameter to worry about. I shouldn't say worry about, that you have to deal with. And so, here's a slightly different way to think about how this drift term model comes about from what I originally had in the notes. So, instead of writing our initial model like this, notice how we have a mu there. I'm going to write it so I have mu sub t, mu times t, I should say. So what this is saying is that things are changing in terms of a function of time. Essentially, the mean is changing as a function of time, to some respect. Okay? Mu times t. And so now if we go through the usual math with this expression here, look what happens. I take 1 minus b times x of t. I get x of t minus x of t minus 1. And then I take this 1 minus b times the mu times t. So that 1 times mu times t is just mu t. But look what happens with the b part there. B times mu t. If we think about what that b is actually meaning, backshifting that t, then that means that b times t is t minus 1. And if you continue going through some of the math, look what happens. I have that extra mu that's in there. And that's essentially then that delta. Okay? So that's basically how this model is coming about. Just a little bit of a different way than I had originally put in the notes. And one reason why I wanted to point this out is that notice that t there. So t in terms of us, when we're actually estimating the model, means t is equal to 1, 2, 3, 4, all the way up to n. Now, if you remember the notes, how do we account for the drift term when we actually estimate the model? Well, we use ARIMA again, but then we also add a particular argument called xreg. And what was xreg? 1, 2, 3, all the way up to n. Why? It's because of that right there. Okay? So that just gives you a little bit more insight. Now, the second subsection dealt with model building. So in other words, what we want to do is, given a time series data set, we want to find the most parsimonious model possible that best estimates x of t. And so this is a common thing all over statistics that, You're given some data. You want to figure out what's the best model for the data. Well, now here it is in terms of the concept of time series analysis. And typically in any kind of model building process, you're going to have certain steps to follow. And so these are the steps that I've come up with, obviously with respect to what you see typically presented. And so the first step then is, well, we check for stationarity, much as we have before. Look at a plot of x of t versus t. Also look at an ACF plot. If needed, you might need to make a little transformation of x of t, like maybe take the log transformation. Then once you got something that you feel as though seems to be stationary, then you look at the estimated ACF and estimated PACF of the possibly transformed x of t. From that, you could choose some models that might be appropriate. Step 3, you estimate these models. And then step 4 is basically what's new for us in this particular subsection, and that is investigate diagnostic measures. So now we have some potential models. We want to figure out, do these models work or not? Meaning, are the particular mathematical assumptions satisfied? Do we have any observations that are, let's say, unusual in nature? And so here are the tools that we have available to us. Now we calculate the ACF and PACF of the residuals. What that's going to allow us to do is look for patterns. If we don't see any patterns, if, let's say, all the values are non-significant, then that suggests to us, hey, this model seems to be okay, at least with respect to this particular measure. But instead, if we have, let's say, a significant autocorrelation at, let's say, lag 1, that says, uh-oh, our model has not fully taken into account the dependence that exists in our data. I need to make a change then to that model. And the type of change that is made corresponds to what's suggested in terms of the patterns that exist in the residual ACF and PACF, such as, if I have a tailing off or if I have a cutting off, I use those same kinds of tools as we've seen before with just the regular ACF and PACF to make judgments about how to change the model. Then we look at a plot of the standardized residuals over time. And we're looking for two different things here. First, do I have any extreme outliers? Second, do I see any patterns? Like if I have, let's say, 10 standardized residuals in a row that are all positive, that says, wait a second, my model is underestimating some stuff. I better make some changes. We look at the normality assumption. We have two tools to do that, a histogram, a QQ plot. And I have to admit it can be somewhat difficult to come up with you look for large deviations from normality before you say, hey, I have a normality problem. We have some examples coming up later today that further emphasize that point. Then we look at what's called a Jung-Box-Pierce test on the residuals, where we look at, let's say, up to lag, let's say 5. Do I have any significant autocorrelation left? Up to lag 10, do I have any significant autocorrelation left? If I do, then that says the model needs to be changed. And lastly, we can do hypothesis tests for the phi and theta terms. And this can actually be an iterative process where, let's say you have a candidate model, you find that there's some problems with it. Then, based upon what you see in these diagnostic tools, you make changes to the model. And then you go through these diagnostic tools again. If everything looks fine, okay, then you can move on to step 5. But if it doesn't, then you might have to make more changes to that model that you were working with originally. Then step 5, for each model that makes it through step 4, pick the best model based upon model parsimony, meaning the lowest number of parameters that you need to estimate. Also, we can look at the AIC. And then step 6, wow, this isn't really part of model building. I just like to put it there because in the end, that's what we want to do with these models. We want to forecast. Okay. Now, if you remember in the notes, there were a number of different steps, or I shouldn't say that. There was a lot of different code that you needed to use to go through that step 4 for the diagnostic measures. What you will see in the next subset of notes, and also a little bit here today, is I've written a function to help simplify your lives. In terms of one function will basically do all the computations needed, at least for one iteration of step 4. Okay, so that's a really brief review of the material for today. Were there any questions? Okay, so on Thursday, for our class, for our regular help class, we will not be in here. The reason being is because there is an event here going on at UNL for high school students, and the person who's running the event asked if they could use our room for that in the morning. I said sure, that was fine, and so they found us another classroom. It's just Plant Sciences Hall 275. In case you don't know, this Keim Hall is attached to Plant Sciences Hall, which is right that way. And so to get to room 275, all you need to do is go out our door, take a right, and just follow the hallway all the way over to the other building, all the way around, and eventually you'll run into 275. Okay. So just as a reminder, project number 3 is due on Thursday, 8 p.m. We've thoroughly discussed that project. Were there by chance any questions at this time that you would like to talk about regarding project number 3? Lastly, before we get to the main thing here today, so project number 4 will be the last project of the semester, and we will start discussing it next time. And basically what it's going to allow you to do is now go through the model building process with 2 data sets. The earthquake data set, and also that Shiny app data set that we first saw in project number 1. And in my notes, so far you've seen that there's a AR1 example for model building. In the next set of notes, the next subsection, there will be an ARIMA 111 example for model building. But I would like to here now for the rest of today, go over one more example. And so these 3 examples are going to really help you then deal with the model building for the earthquake and Shiny app data. Okay. So we're going to talk about radon detection. The stuff that I do here is in a R program that I posted to my course website called week10.r. The corresponding data that we're going to be using is in week10.csv. Okay. So if you don't know what a radon is, that's okay. Let me give you a brief explanation. So radon is a gas that is not good. It's not good for you. It's odorless, meaning that you cannot actually smell it. But it can exist, obviously, in the air. And it happens to be the second leading cause of lung cancer in humans. First being, tobacco smoke. And I think starting about 20 years ago, the Environmental Protection Agency, or EPA for the government, started wanted to make people know about the problems of radon. This radon is a gas, and somehow it exists in the ground, in the dirt. And while if you're outside, it's no big deal. But if you're, let's say, inside and somehow, let's say, some of the gas is able to seep in the building that you're in, then that gas can build up. And this is especially a concern in Nebraska, where most houses have basements. The basement obviously is in contact with the dirt in the ground. And this radon gas can build up in people's homes, especially in the basement area. And over time, that could be very harmful to you if you're breathing in that gas. The EPA has set up a particular level for what is, let's say, unsafe. If the level happens to be more than 4.0 in their measurement scale, then you should avoid that kind of a setting. And so, a few years ago, then I decided to have my home tested for radon. Was there a problem? And so what's done is there's different ways to have tested. The best way is you call a professional radon mitigation service. And they will come out to your home and they will set up a device that takes hourly readings of how much radon is in your home. And they'll set it up in the basement. And so here are the readings that I had a few years ago when I had this done. Let me make this just a little bit bigger. Oh, why not? Let's go 200%. So at noon, I had a reading of 4.7 in my basement. And that is greater than the 4.0 that the EPA says, hey, you got a problem. Then it went up to, at 1 p.m., 5.8. If I page down, look what's happening at night. It's really getting high. Okay? And this detector or measurement tool was used for a few days. And the last reading was at a reading of 11 at 3 a.m. And so the person who was running the test, when he came back, showed me these readings. He says, you got a problem. You got to take care of it. Now, something that he probably wasn't expecting was when he was showing me these readings, I was getting really excited and happy because I was thinking, whoa, this is just like time series data. I could use this with my students. I said to him, can I have that sheet of paper that has all these readings? And he said, yeah. Most people just throw it away. Or I just usually throw it away. And so I got this. And so what we're going to do is take a look at the data with these time series analysis methods that we've talked about here. So let's find the best model. So step one, let's examine stationarity. And so let me go over here to my program. So I'm going to read in the data like usual. Oops. Let's see. Maybe I already read it in. Yes, I already did read it again. Okay, so that's all my reading. So we have, I think it's about 89 or so. And so we're going to do a plot of the data, just like what we've done in the past. If you want me to go through the code, I'd be happy to. But this is what the plot looks like. Okay. So we can see that there are changes through time. But what we're looking for, first of all, is do I have any problems with stationarity? What do you think? Yes or no? So we worry about the mean. Do you think the mean's changing through time? Yes or no? I'm having people shake their head. No, that is correct. You are correct about that. So I don't think there's any non-stationarity with the mean. What about non-stationarity with respect to the variability? If you see where my mouse is, you might be a little bit concerned about right here. But typically what we should do is, look for much larger issues than just 3 times. Well, yeah. At least 1 time point. It's a little bit unusual. Maybe these 2, but notice we have something here. We have something there as well. And so I don't think that there's really any problems with non-stationarity in the variance. I think it would be really too picky if I was saying that there was. Okay. So we have another tool available to us. We can also look at the ACF. And whenever I do the ACF, when I'm doing model building, I also do the PACF exactly at the same time because the next step is going to require that. So I'm going to use the ACF here. And let's take a look at the ACF. What are we looking for in these situations? We're looking for, let's say, large autocorrelations that persist over time. I'm sorry, persist over the lags, excuse me. We don't have that here. So I think this confirms, we don't have problems with non-stationarity in the mean. Okay? So that's good. Okay, let's see here. Oops. So the next step, choose a few ARIMA models to investigate using the patterns that you see in the estimated ACF and PACF. Okay, so give me a model. What do you think? We obviously have a significant value at lag 1 for both plots. And again, we're looking for cutting off, tailing off in these kinds of plots. And I would tell you there's more than one model that one could suggest here. What do you think? ARIMA 101. Why? Yeah. And so I think what you're saying is that after lag 1, we are tailing off. It's a little bit questionable, but I definitely think an ARIMA 101 model would be something I would start off with. How about other models? So having non-significant values after lag 1 make it kind of hard to say that P is greater than 1 and or Q is greater than 1. So then that leads us then to situations where maybe one of the P's, one of the Q's could be 0. So for example, you could think of, let's say, that ACF plot tailing off starting at lag 1. Look what we got here. This, if you see where my mouse is. And then maybe this is all kind of, you could say, oh, I'm going to use a non-statistical term here, garbage, in terms of values that are essentially about 0. If this was truly tailing off, that's what we would have to assume. And then maybe this is significant at lag 1, and it's cutting off to 0 after that, because these are all non-significant. That's just another way to interpret this. So that interpretation gives us then in ARIMA 100 or AR1. And you can sort of make the same kind of judgment the other way, you could say, with respect to a moving average 1. Maybe this is tailing off. I'm sorry. Yeah. Maybe this is tailing off and this is cutting off. If you see where my mouse is. So you can see how there can be multiple interpretations. That's fine. You have multiple models. And in the next step, we'll evaluate all the models that you chose here. And look to see if we need to make changes to them. Okay. So that's basically what I just said. So step 3, what did I do there? Estimate the models. So of course we just use the ARIMA function. So the ARIMA 100. Oh, notice how we have order 100 there. And so I'm just going to go ahead and estimate those models real fast because it's really nothing that we haven't seen before. Notice I'm putting them into mod.fit1, mod.fit2, mod.fit3. Okay. So step 4 now, we want to do these diagnostic measures. And that's the main thing that was new in this last subsection for today. And so described in the next set of notes, there is a program that I've written called examine.mod.r that contains a function called examine.mod, which basically does all the computations for you automatically. In my video, I explain the function in more detail. We're just going to use it here so we can evaluate our model. Now, the way to use it is that, so all the code is in, there's the actual program itself. I need to somehow get this code into R. One way is you open up the program in Tin or RStudio and you just simply run all the code. Another way, if you've never seen this before, this can be helpful, is that there's a function R called source. And what you can do is, in the file argument, simply point to where that program is. And when you run it, R will automatically run everything that's in that file in your R console. Okay? So it's pretty slick. And so to run this examine.mod, so once I have it available to me, this function, then the first argument is, well, where is my model fitting information from ARIMA? So it's in mod.fit. And then I have a way to name the model that I'm looking at. I purposely do that here because I will often be running this function for multiple models. And this label, as you will see, is going to be printed on our plots that we're going to be looking at. And so it helps remind me what those plots are for. And then I have a way to set, well, how many lags do I want to look at when I'm doing some of these tools. And so let me go ahead and run this. And what you're going to see once I run it is you're going to see two different plotting windows coming up. And there we go. Okay. So this is for the AR1 model, ARIMA 100. Is this big enough that you can see it? Yes or no? Okay. So let's look at the plot in the upper left-hand corner. So that's a plot of my standardized residuals versus time. Do we see any problems? First of all, let's think about it in terms of outliers. Are there any outliers? Anything that we should be concerned about? Yes or no? Probably the largest standardized residual is about a +3. Okay. We have maybe another one about 2.5, maybe a third one, 2.5, 2.7. We have a sample size of close to 100. Would that be unusual to have those large in absolute value standardized residuals with a sample size of 100? Yes or no? Yeah, I agree. No. You know, we should, if we have purely a normal distribution, 1% of your observations will fall outside of plus or minus 2.576. Okay. Here we have at least 1, maybe 3. That's not that many more than 1. And so I think I'm okay with these residuals. Also, we look at this particular plot then to determine, do I have any, let's say, trends over time? Do I have any situations where I have a lot of positive residuals in a row or a lot of negative residuals in a row? And it really doesn't look like that occurs here. So based upon this first plot, looks like things are going good. Next, we can look at the ACF plot of the residuals. What do you think? Thumbs up or thumbs down? Thumbs up. Any other thumbs up? Come on, give me the thumb. All right. Yeah, this is good. I'm happy. All those, remember at lag 0, of course, that value will be 1. Okay. Then my Jung box Pierce tests for these autocorrelations. So what's plotted on the y-axis, corresponding to the y-axis, is the p-value. So for example, at lag 10, my p-value is 0.8, which says that there's not sufficient evidence to indicate that there is autocorrelation amongst the residuals when you're using a lag 10 or lower. So all those p-values are quite high. So again, hey, this is looking good. This is looking good. Let's go over to the next set of plots. PACF. What do you think? Thumbs up or thumbs down? Thumbs up. Yeah. No significant values. Now, what do you think about the histogram of the residuals? So we're looking at for normality here. What do you think?
It should be fine given the sample size.
Yeah, I agree. Well, yes. When I first saw this, I was a little bit concerned. You have this bar going up, although it's kind of going up in a nice spot where you would want it to be in the middle. And, basically, if I took some stuff that was in this bar and put it down here, things would be looking better. One thing you always have to be careful about is that these kinds of plots can be a little bit distorted based upon what you're choosing for the bins or the classes that form the histogram. So, I could do a different histogram that has, classes maybe a little bit wider. And maybe this, you'd be a little bit less concerned. But, if you notice out here, we have some larger ones. Note that this is just the residuals themselves, not the standardized residuals. Okay. I have some residuals that are coming way out here. What are those? Well, it's these where you see my mouse. Those are the 3 that are causing this right here. Okay. What do you think about the QQ plot? So again, what we're looking for here is that we want these points to fall on the line. Deviations from the line suggest possibly you have some normality issues. What do you think? Thumbs up, thumbs down, thumbs to the side. Oh, I saw one thumbs up. Notice that these, where you see my mouse, those 3 points correspond again to what I was pointing out before. So we do have a little bit of deviation from the line. QQ plots can be difficult to interpret at times because it's much harder to estimate quantiles well when you're at the extreme of the distributions, especially given like a sample size of 100. And so if there's any deviation at all, I would always expect it into what one would refer to as the tails of the distribution. The tails are exhibited by the edges of what you see here on the plot. And so what you see also on this right side is what we were seeing right here. Okay? Now, the way that I typically interpret these plots is I always look for large deviations before I say that indeed there's a problem. I'll give you 2 examples of this. So a number of years ago, my advisor at a conference decided to I think he put something like 6 or 10 QQ plots together, put them on a big poster board. And he asked people, I guess maybe as they were coming into like a room for a presentation, tell me, look at each of these plots. Which one of those corresponds to where you had a sample that wasn't from a normal distribution? And so there was a variety of different answers. And then after everyone came in, he said, guess what? They're all from a normal distribution. So even though people were actually saying that one wasn't normal, that one wasn't normal, and so on, they were actually all from normal. And that the reason why I tell you that is that you have to be very careful interpreting these plots. You can't be too picky. So let's actually take a kind of motivated by that, what my advisor did. Let's actually generate some QQ plots here. Okay? I'm going to set a seed so I can reproduce my results. We actually have a sample size of 88. And normally we think of 88, that's a pretty large sample. You know, I should have a good representation. But again, we're looking at the entire distribution here, not necessarily, let's say, like the mean or some summary measure of the distribution, which is what we're often most presented in many stat courses. And so to do the QQ plot, so I'm going to simulate data from a standard normal, 88 observations, put it into norm. Then I use my QQ plot code that was given in the notes. And let's go ahead and run that and see what the plot looks like. Okay. So in this case, there really isn't much deviation from that red line. Again, we do have normality. Yeah, we have a little bit up here, a little bit up there, but remember, we should conclude that everything's okay. So that was with that seed number. And now let's just have R itself randomly simulate some data and see if we get as good of a plot like what we just did, or if we get something that makes us worry about normality. Okay. A little bit more worry. Notice what's on the right side. We're having more deviation. But again, we have a normal distribution in the end. So let's see what happens for another case. More deviation. You know, I thought about before coming to class, I'll just fool around with some C numbers and eventually come to some cases where it looks like, yeah, you don't have a normal distribution from this plot. So I could actually show it to you. But I thought, oh, let's leave it up to chance and see what happens. Maybe R will end up choosing using its internal C number calculation, and maybe it will come up with something. And I think we've had 2 cases now that, yeah, it looks like we have an issue, even though we shouldn't. Let's do another one. That looks pretty good. Yeah, it looks pretty good as well. Yeah, we're having some coming off that line. I mean, look how far that point is off that line. But in the end, we really shouldn't have a problem. And so the whole purpose of this short little demonstration is don't be too picky. Look for very large deviations. Let's actually do a case where we would have a large deviation. Give me your favorite distribution that's not normal. We'll simulate some observations from it. I am assuming that all of you do have a favorite distribution. Oh, well, let's do something skewed. How about a chi-squared with degree of freedom 1? Let's see what happens. There we go. Now we're talking. So we have normality issues. You know, chi-squared degree of freedom 1 is extremely right skewed. Here, I can do a quick little plot. Sometimes it's not really presented well when you see it in a class when someone just draws it out. Let's see, x equal x. Let's see, we'll go up to 10. So there's the chi-square 1. Okay, definitely not normal. Okay. So it looks like, oh, actually we have one more thing to look at here. Hold on. So it passed all the everything in terms of the plots. We can look at the corresponding p-values, which are automatically generated for us as well. So for the phi1 parameter, the test statistic's 2.85, using a standard normal approximation to get a very small p-value. Okay, so this is saying that phi1 is significantly different from 0. So it looks like then this ARIMA 100 passes all of our diagnostic measures. Let's see what happens with these other models. We'll try to go through them a little bit quicker. So now this is the moving average 1. I don't know why this is doing that to me today. Yeah, let's put everything in the same order. Okay. So let's look at all the plots on the left. Standardized residuals look, I think, okay in terms of the size of the values. It's just starting to get a little bit concerned here. Notice how I have 4 in a row for these negative values, but that's, when you have a sample size of 100, it's not. I don't think it's necessarily unusual to have 4 in a row that are like that. I'm not really too concerned. ACF looks good. P-values for Jung-Box tests look. Jung-Box Pierce test look good. PACF looks good. The normality issues, I guess similar conclusions as before. Let's look at those p-values. We have marginally significant value for the theta 1. Let's look at now. Let me close it out so we don't confuse these. Let's look at the ARIMA 101. So now I have 2 of these parameters for the ARIMA for phi1 and then also theta 1. Standardized residuals look good. ACF look good. Jung-Box Pierce tests look good. Yeah, everything seems to be fine. Let's take a look at the significance of these parameters. And now look at that. So marginally significant for phi1, for theta 1, p-value 0.45. Okay.
These are for the residuals.
Well, these p-values are for the actual model parameters. Okay. And so what this is saying is that this theta 1 is not significantly different from 0. So this is making me start to be concerned about, do I actually need 2 parameters, in addition to sigma squared and mu? Do I need 2 parameters to account for the dependence? So it's making me concerned. So what one could do there, well, I guess what I would do, even though it didn't pass, let's say, everything, I would still carry this model over to step 5 of the model building process and see what happens there. But now I'm starting to have doubts about this model because there's maybe one additional parameter that we don't need. So let's go ahead and now take a look at the AICs. And this is what we get. So which of the models is best according to the AIC? What do we look for? The lowest value, and that is then that first model. So the AR1. So based upon these model building techniques, I would choose then the AR1 model. Now, this particular example with this data is probably a rather simple model building exercise, because I found models, at least 2 models, that looked like they were okay. But if they were not okay, I would have had to go back to those models and then make changes to them. So, unfortunately, off the top of my head right now, I don't remember if this is in the notes or not. So, please take note of this. And what a model building technique that people often use is they will be conservative first in terms of choosing models. Rather than, let's say, jump to an ARIMA 505 model, they're going to first do maybe an ARIMA 101 model or 100 even model. Start there. Look at the corresponding residuals. If those residuals saying you haven't fully accounted for the dependence, well, let's start adding some AR terms or AR parameters. Let's start adding some moving average parameters and start building the model like that until you get to a point where the dependence seems to be taken care of. So that's let's say another kind of strategy with all built in this that one could follow. And the reason why I tell you that is, again, because this radon example is fairly simple in the end. But project number 4, it may not be as simple. And so you might have to think in that manner of, let's make a change to the model, see what happens. Make another change to the model, see what happens, and so on. Okay? Okay. Any questions? Yes?
If the AIC is lower on the ARMA, would you choose, which one would you choose?
Well, yeah, let's say that the AIC was lower for the ARIMA 101 model. Then I probably would lean towards using the 101 because the AIC is essentially, it will penalize you for having too many parameters. And so if the AIC is still lower, then that tells me, even though what that hypothesis test gave me, that perhaps I do need that extra parameter. Now, I would still find it very doubtful that that would happen, though. Perhaps if that p-value for that theta 1, instead of being 0.45, which is pretty large, if it was more like 0.1, then that wouldn't surprise me to see that happen with the AIC. In the end, though, you would have justification for multiple models. Okay? The AIC, while it's a nice tool, it's not necessarily a perfect tool. And I know I have it in my notes that maybe we will look at this in class, where let's see if the AIC gets the model right. Well, we have a little bit of time. When we talk about that, how would you, and this is more of a research topic, how would you actually figure out, does the AIC actually work? How could one maybe use Monte Carlo simulation to make that judgment?
Try over many cases.
Yeah. Suppose you set a particular model that you're simulating from. Let's say in ARIMA 101. Okay. Then what you could do is simulate, let's say, 1,000 data sets. For each data set, you fit a variety of different models. Maybe you set up a for loop or multiple embedded for loops where you cycle over, let's say, p equal 0 to 5 and q equals 0 to 5. Each time, estimate the model, get the AIC out. Then look at for each 1,000 data sets. So for each 1,000 data sets, you're doing this for loop. For each of the 1,000 data sets, you look at what was the model chosen. Was it P equal 1, Q equal 1, or was it something different? If it's something different, it tells you the AIC got it wrong. So it will be interesting then to examine how often the AIC gets it wrong. How is that related to sample size as well? Because you would expect that the larger your sample is, the more representative that the more representative that data will be of that corresponding model. So you expect as the sample size goes up, the AIC should be also improving. And so one could use a Monte Carlo simulation study, and I've actually seen it before with these ARIMA models, to do something like this. And maybe in one of these Tuesday classes we'll investigate something like that as well. Okay. It was actually something I almost put on project number 4. Any other questions? Okay. So what's next then for our class? I'll be available for questions. You have a quiz, of course, that's due at 8 p.m. On Thursday, I have my usual office hours in, sorry about that, in Plant Science Hall, room 275 at 8:30. Then the help class will be in that same room at 9:30. This will be a great time if you have any last-minute questions regarding the project. I'll be available to answer them. You can maybe put your final project together as well with your classmates. The project's due at 8 p.m. on Thursday. Then next Tuesday, we'll be back in our normal room. We'll have office hours. We'll have a class at 9:30. The material is 2 subsections. Subsection 14 is the second half of model building, where we go through an ARIMA 111 model example. Section 15 now starts what are called SARIMA models. And I briefly mentioned them before in our class. That extra S that's at the beginning stands for seasonal. So if you have data that's, let's say, observed over quarters or over months, across many years, you might expect, let's say, January of 2023 to be related to January 2024. But if I have monthly data, that's separated by 12 time points. How do you handle that? Well, we basically have an addition to our ARIMA model that allows us to handle those kinds of situations. That's why it's called SARIMA models. This material corresponds to sections 3.7 and 3.9 of our book. We will also discuss project number 3, the grading that from that. We will introduce project number 4, and there will be the usual quiz due on that Tuesday. So looking further ahead, project number 4 is due on Thursday, April 18th, and then we have a test coming up in 3 weeks or so on April 25th. Any last questions? Okay, that's all here for today.